بسم الله الرحمن الرحیم. چهارمین وبینار شاخه محاسباتی انجمن فیزیک ایران رو امروز انشالله خدمتتون هستیم. سخنران امروزمون جناب آقای دکتر آرمان شفیع از مؤسسه استروفیزیک و علوم فضایی کشور کره جنوبی هستند. آقای دکتر شفیع دوره کارشناسیشون رو دانشگاه صنعتی شریف گذروندن. دکتراشون رو تو دانشگاه IUCAA در کشور هند بودن. سال 2008 دکتراشون رو گرفتن. یه دوره پژوهشی 2 ساله دانشگاه آکسفورد انگلستان بودن بعد از اون، و از سال 2014 و از اون به بعد از سال 2010 به بعد جاهای مختلفی در کره جنوبی مشغول پژوهش بودن که از سال 2014 به بعد عضو هیئت علمی مؤسسه استروفیزیک و علوم فضایی کره جنوبی هستند و خوشبختانه امسال هم اخیراً یک جایزه خیلی خوبی به عنوان جایزه علمی برتر سال 2020 انجمن نجوم و استروفیزیک کره جنوبی رو برنده شدن. از ایشون تشکر میکنیم که سخنران ما هستن و پذیرفتن سخنرانی کنن. خدمتتون هستیم آقای دکتر شفیع.
ممنونم بابت معرفی و ممنون از صادق عزیز و همه دوستان بابت اینکه دعوت کردن منو. ببخشید بابت این مشکلاتی که اولش پیش اومد. خب تاکی که امروز میدم در مورد بیشتر کیهانشناسی و مشکلاتی هستش که ما باش برخورد خواهیم کرد. منتها متاسفانه به خاطر اینکه ترجیح میدم توپق نزنم تو حرفا، سعی میکنم که تاکو کلا به انگلیسی بدم، چون نصف و نیمه بهتره که آدم صحبت نکنه. ببخشید منو تاک بخش زیادیش همین حدود چند هفته پیش بود فکر کنم در IPM مشابه این تاک رو دادم. این تاک فعلی یه سری مسئله اضافه تر داره نسبت به اون تاک که بیشتر برمیگرده به نوع دیتایی که ما در واقع آنالایز خواهیم کرد، بررسی خواهیم کرد توی سروی ها و توی تلسکوپ های نسلی که دارن میان. یعنی نمیگم نسل آینده یا نسل دور، نسلی که به قول معروف آینده نزدیک هست توی دهه 2020، یعنی از 2020 از الان تا 10 سال آینده. امیدوارم که تاک خوبی باشه و قابل استفاده باشه. خب بخش اولش که بیشتر در مورد کیهانشناسی است رو سعی میکنم، اصطلاحات زیاده ولی خب سریع بگذرونم و برسم به جایی که بیشتر در مورد نوع دیتا هست و سعی میکنم تاکم را هم حدود نیم ساعت 40 دقیقه‌ای تموم بکنم و بتونیم با هم یه صحبتی آخرش داشته باشیم. خب شروع میکنیم. It's about 30 years that we have entered the era of the precision cosmology, which practically started by being able to observe the universe. And it comes practically after lots of technological developments that we were basically, we could make large telescopes, building very big mirrors, and then there were advancements in the electronics, like making the CCDs, and we had optical fibers, and so all these developments and technological advancements helped us to make better telescopes. We could send satellites to the space, so they allowed us to observe the universe better, and combining some theoretical works with the measurements at the same time, being able to run heavier simulations. We were also advanced in developments of the faster and more accurate CPUs, allowed us, to develop a lot in the field of astronomy and astrophysics. So practically the era of precision cosmology started about just a few decades ago, and so far it has been going pretty well. One of the key problems, or one of the key issues in the field of cosmology, has been to study and to understand and at the same time verify the standard model of cosmology. فقط یه چیزی، من هر 3-4 دقیقه یک بار یه سوال میپرسم که آیا شما صدا تصویر من رو دارین یا نه، چون من فقط اسلایدهای خودم رو میبینم.
صدا داریم آقای دکتر، صدا داریم، خوب دیده میشه.
So standard model of cosmology is a combination of the FLRW metric because it's based on the general theory of relativity, and we have isotropy and homogeneity of the universe, so you can find a very robust solution, which is a full W metric. Then we assume the universe is flat. We assume that we have dark energy, and dark energy is cosmological constant. We assume dark matter is cold and weakly interacting. We assume polar form of the premodal spectrum, and go on. We have the one parameter for epochal reionization, and we have Hubble constant, which is a very important parameter in this model. So it's a very simple model, describable by just 6 parameters, and it's a model that has been survived for a long time. So as it is a combination of assumptions, one should realize that it's these are very reasonably good assumptions. The status of the standard model in 2020 is very strong. 20 years ago, when Rees and Perlmutter did independently from Harvard and Berkeley discovered the acceleration of the universe looking at the Type 1a supernova, we had only 60 standardized supernova Type 1a, and now we have about 1,000. So in about 20 years, we have we have more than about 15 times more number of the calibrated supernova, and the results are very consistent with the standard model. As you can see that the residuals look very good, and they show no specific deviation at any redshift. We have the similar case for the case of the cosmic microwave background. Things has developed a lot. About 20 years ago, we had almost nothing. These are all different surveys which were trying to detect cosmic microwave background, and they were basically struggling to find out the first acoustic peak. The first acoustic peak was practically detected around 2000, 2001 by Boomerang and Maxima. But now we have Planck, which is a space-based telescope, and now we can see that how far we can go in the angular power spectrum. So this is marvelous. I mean, this is amazing how fast we could develop in technology. That in 1998, many of us who remember the World Cup in 1998, we know that it's not that far away. Maybe for my generation. At that time we had nothing, and now we have such a beautiful, clean, nice data. We have also band acoustic oscillation by just mapping the galaxies in the universe. These are some of the results from the latest compilation of the extended bus survey. There's a final cosmology results, which was released just a couple of months ago. I am also a member of this collaboration involved in this paper. And things looks fine, things looks like that, we have a good consistency with the standard model. And by looking at all different, tracers like LRGs, ELGs, quasars, and it's also consistent with the lambda model. Remember that the BAO is a blue one, so it's consistent with the W equal to -1 and the reasonably amount of the matter density. Of course, one can notice a kind of a slight tension here, which I think is an important issue. I'm not going to talk much about that, but this is something that now people are looking at to understand what is really going on. So as I said, we have the final results of the BAO and everything looks fine. It's like a flat universe with the low value of H0. Everything looks good. So standard model cosmology seems to be a combination of reasonable assumptions. So it's a combination of assumptions, but these are very well taught reasonable assumptions. Let's remember that the cosmic constant is a constant in Friedman equations, and it has been there for a long time. And so it's something that has been there, and it's a seriously very strong candidate. The flatness, at the same time, polar form of the premodal spectrum, it is something that is supported by the simplest models of inflationary scenario. So these are not sort of assumptions that we are just they are not totally ad hoc. We have some base for it. At the same time, FLRW, as I mentioned earlier, it's a very stable solution of the GR plus isotropy and homogeneity of the universe. And we know that, by observation, cold dark matter is weakly interacting. So these are reasonable assumptions. But the problem is that there have been persistent tensions in the standard model. and this tension has been increasing, fortunately or unfortunately, to my opinion, fortunately, in last 7 years or so. In fact, the tension started to show its face in the first conference of the Planck in 2013, which was very surprising when I remember George Statue come and says that, yeah, I mean, we got the H0 of the 67 plus minus something like 1. And at that time, the Adam Rees group were measuring H0 to be about 72.5 or something. So with the WMAP, it was pretty okay because WMAP H0 was about 70, and the error bars were practically overlapping each other. But suddenly Planck shifted things to the lower side of the H0, and it shows inconsistency with the local measurements. So this is some mainly recent results from the most recent analysis of Adam Rees, with their extended catalog of looking at many different Cepheids and supernova at a very low redshift. And we see now that the Planck data plus flat lambda CDM model predict the Hubble constant to be about 67. And the late observations has shifted to about 74. And the error bars shrink. So now we have already more than 4 sigma tension. And this is something very important because, if you have to understand what is really going on. Is it really due to some new physics that you have to find, or it is some systematics in either of the data, or should we really extend our current model? So these flashes practically shows that how we can improve things by extending the standard model. Here we are assuming that the equation of state of dark energy can vary by adding 2 degrees of freedom. Here they are using the CPL, Chevalier-Polarski-Linder ansatz. Here is when you assume that you can have some extra number of effective neutrinos. Here you allow curvature. Then here you have a dark matter interaction, dark matter neutrino interaction, and here is about the early dark energy. So some of these models can reduce the tension, but I will mention later that these reductions are sort of artificial in many cases. And it's not only about the H0 and the CMB. We have this tension amongst some other data as well. For instance, here is a paper last year I had with one of my ex-postdocs, Xiaolei Li, that you can clearly see that combined data in the standard model have this red contour, but when you add CMB, you suddenly shift the center of the contours extensively to the other side. And in 1D probability distribution function, you can see that things are not really good. Even the 2D, it might looks like that, they're consistent, but in reality, they are marginally consistent with each other. So which shows a kind of a tension. Which shows something that, okay, something is really going on. And we had also the case of the shear and lensing, that the sigma 8 omega matter contours are, very vaguely and marginally overlap with the constraints from the Planck. So yeah, things have been there, and these tensions have been there. I would like to say something funny about the Xiaolei. Xiaolei is actually got a faculty job in the Hebei Normal University, and Hebei State was in fact where the corona started. So in February, we were feeling so pity for her that she was stuck at home, and things were very dangerous in China. But now China seems to be the most safe place. I can see that they are going to work, and everything is back to normal. So I hope that the normality goes back to whole world soon. Okay, how to go beyond the standard model of cosmology? So I just categorize things in 3 main categories. That we need to find features, deviations in the data beyond the flexibility of the standard model, using model-independent reconstruction. It is one of those things that having a good amount of high-quality data would be very important. That's why many of these, litmus tests or null tests would be more appropriate to be implemented on the near future data, not the current one. We can't focus the power of the data to, as I said, to test with a litmus test. This one was about the deviations features. And then we can also find tensions among different independent data, assuming the standard model, making sure that there is no systematics. So this is something that, it is very important because, it can basically let us know that if we are looking for systematics or we are not looking for systematic. And from the theoretical phenomenological side, it is important to, if we can, introduce a new model that can explain the data better. But better means that it's statistically significant, means that not by having just more extra degrees of freedom and having a better likelihood or chi-square and said, okay, look, my model fit better because I have a bigger contour. So this significance is actually very important. And it would be very difficult to beat lambda CDM model because lambda CDM model is already a very minimal model. It has only 6 degrees of freedom, and no degree of freedom for dark energy, no degree of freedom for curvature, no degree of freedom for properties of the matter. So it's a difficult model to beat because it's very simple and it's very minimal. And when we want to compare statistically models with each other, we usually use Bayesian evidence, and Bayesian evidence prefers a simpler model. So it's very difficult to beat this model statistically. There have been some works again, so I'm just trying to go through all these 3 different things that how to do that: finding features, falsifying, and finding tensions. This is, for example, a null test that we developed about 6 years ago on the first quasar data from the BOSS collaboration, SDSS3. And we noticed a tension between the CMB measurements and the BAO measurements in a model-independent way, which was interesting. Without its systematics, but things really didn't change much in the last 6 years, and this is the final data release of the SDSS, and the tensions are still there. We can basically compare different data assuming a particular model. This is a collaboration we had with the Gongbo Zhao. At that time, I was not a SDSS member, but we collaborated in this paper, and basically they used KL divergence to quantify the degree of tension, and yes, it was nice to see that in fact the Lyman alpha BAO data is indeed in tension with the standard model, and H0 we knew before. So seems that these tensions are there and they are serious. There have been reanalysis of the data which we had, and things practically confirmed each other. In the case of the H0, things become worse because risk analysis were about 73, 72, but the risk 2019 shifting to 74. So situation has become worse. So here it seems we have multiple suspects. You have a large group of models which seems all having a problem with each other, and we don't know what is the problem. We don't know if there is a systematic in either of the data. We don't know if we need to go and have a new physics. We might need more neutrinos, early dark energy. What should we do? Late dark energy. So we have a multiple suspect to answer to this, to this dilemma. I mean, I'm using this picture from this very classic René Clair movie, which based on Agatha Christie, that there are some guests in an island, and mysteriously one after one they are dying, and we don't know who is the killer or who are the killers. So at the moment in cosmology, we have a very similar situation. We don't know where to put the blame. Is it on dark energy? Is it on early universe physics? Is it on neutrinos? Is it on some systematics? So we have to be very open-minded. How to resolve the tensions? Well, we need we can think of statistical fluctuations, but not anymore, because at more than 4 sigma, it can be, it would be very rare to have it because of the statistical fluctuations. What I bet for mainly would be systematics in one or some of the data, and this is highly possible considering the complications of the tensions. In fact, one of the results we had last year was that these tensions are not resolvable by minimal modifications. So it means that it's not really possible to make a minimal modification to a standard model and resolve all the tensions. And a model that is needed to resolve all the tensions would have a very weird characteristics, which may look very unphysical. So this is something that hints that there might be systematics over one or some of the data. And there have been extended models and new physics proposed, many papers, which is okay. But mainly these works in a way that they're extended models with more degree of freedom. And having more degree of freedom, you would have larger confidence contours. Having larger confidence contours, which looks like that, there is a better consistencies because there is more better overlap between the larger contours. So it is okay to do that, but it's better to avoid overselling, because if the current observations are reliable, most of these models will be eventually ruled out sooner or later, because central values really matters. So how to change things? So I will go really quickly here because I want to go to the data part. So these are the different pillars of the standard model: flatness, isotropy, homogeneity, dark energy, Pavlov model spectrum. And I just briefly go through that, what can we do to make things better. Let's say that let's go to the dark energy. I'll just introduce two works, one Komnikovsky's group in run a campaign that, they basically discuss that, you can have dark energy. By having early dark energy, you can, in fact, decrease the value of the baryon drag epoch, and then, for H0 or the H0. The point is that the model has some extra degrees of freedom. And a couple of months ago, there was a paper by Collins et al., by Hill et al., that Colin Hill et al., that they showed that, well, the model really is that when you combine with all different polarization data and everything, this model's central value, it just shifted from 67.3 to 68.3, which is literally not really much. And your error bars are larger, so instead of 4 sigma tension, you have, let's say, 3 sigma tension. So tension is not really resolved in this early dark energy, at least some combination of the data. There was another work which I did here. We proposed a phenomenologically emergent dark energy. That no dark energy is in the past and acts as an emergent phenomena. So it basically, the model allow lower rate of expansion in the past and higher rate of expansion in the late times. So the work is interesting, and it's a kind of a bet on the future. It means that the model is not supposed to rule out lambda now, but it's supposed to rule out lambda in the near future. And when we wrote this paper last year, many paper comes after us, practically testing the model on different data. And one of them was this work by the Holy Cow group, which they included this PEDE model. And it was interesting because PEDE is one of the only models which can give you the similar value of RS for a larger value of the Hubble constant. So, and also we had some generalized emergent dark energy model very recently that we just tried to come up with a, with a kind of a function which include both models, because PEDE also has no degree of freedom for dark energy. Lambda CDM doesn't have either. So here, PEDE and lambda basically would be two special limits of this generalized model. And for lambda delta equal to 0, we have lambda CDM, and equal to 1, we have PEDE. So now posterior of the delta fitting any data can basically tell us what is really going on, and this is what we did. And we showed that if we just consider CMB and H0, basically these are the two data at the extreme ends with no connection with each other. And so if both data are reliable, the JEDE, well, because emergent would rule out the cosmological concept. We have to see and see what would happen. Briefly, the form of the premodal spectrum. Premodal spectrum, is a very important subject in cosmology as well as theoretical physics, because it's related to the physics of the early years. So there have been many attempts to reconstruct the form of premodal spectrum for many, many years. In fact, this is my first cosmology project, which I did for my master degree in 2002 to 2003, 2001 to 2002. So it's already about 20 years ago. And this is something that we are still working on. And so the form of premodal spectrum is very important for one reason, for a few reasons. One of them is that we don't have to have the form of the power law. Other models can work well. And at the same time, we can basically find theoretical models to explain such behavior. Let's say that for this step model, we can find, one of the Stravinsky models which can fit things pretty well. So beyond the power law, another more important thing is that going beyond the power law, we can have different values for the background parameters. So here we did lots of Monte Carlo analysis to test these models. A collection of the papers with Diraj Hazra, who was my ex-postdoc. Now he's an associate professor in Chennai. Sorry, what's happened? And what was interesting was that, some of the data practically, TTE, these are the polarization temperature data, one of the models fit all the data better than the base model. So that we are studying again, we would have a pretty big paper soon on that. And to just say that, other models are possible. But as I said, when other models are possible, because we are changing the form of the AS and S, then what we get for these background parameters would be also different. And this is actually a very interesting point, because we can do direct reconstructions, and if we allow free form of the premodular spectrum, instead of getting these contours for the background parameters, we may end up in these blue contours in the background parameters, and which basically help us a lot to explain many of the tensions. But practically what it means that, we get these tight contours because we get very tight contours and tight constraints, probability distribution for the H0, let's say here, is because, we are assuming, we are forcing a power form of the premodular spectrum. But if we don't force this assumption, then things can be very different. So these are some recent papers which we had on this topic, that we basically try to fix the background parameters consistent with the R19 local Hubble constant measurements, as well as the Wick lensing data, and then trying to reconstruct the form of premodular spectrum using modified Richardson-Lucy deconvolution, and this is what we got, and which is an interesting form because it doesn't look very natural, but having this form practically make you to end up to such a contour in the parameter space, which is interesting. You are basically very well consistent with the Rees analysis, the lower value of matter density, which allow you to be consistent also with the Wick lensing analysis. I should say that there have been many other attempts by other groups. I know about the ETH group, I know about the Cambridge group, to find a form of premodular spectrum that they couldn't do, and that basically shows the great advantage of the MRL deconvolution to the other methods, because it's able to generate various features with different amplitudes and frequencies at different wave numbers. So it's a very, very unique capabilities of the MRL. So I generally tell people that I don't think I'm consider myself a data scientist, but maybe I can consider myself an algorithm scientist, which to myself is more exciting and interesting, to build up tools, algorithms to extract some very precious information outside the data, and so that's fun. Okay. There were some issues about the high features, which recently with my current postdoc, one of my current postdocs, Ryan Keeley, we could basically show that these high frequency features are not required. We need just these features, and having these features and having a kind of a deformation model which interpolate between the power law and the direct reconstruction, we can basically get the very high base factor in favor of the deformation model when we feed the CMB and the supernova CMB and R19 data. So it is a very interesting new opening for the field. That's why Ryan chose the title from the Star Wars, Inflation New Hope, because that might be interesting even for the model builders to come up with a form of maybe primordial power spectrum, some model of inflation which can generate such a feature. Okay, now I go to the future perspective. If you have any question till now, let me know, or at least tell me that you can hear me and my slides.
خب دوستان اگر کسی سوالی دارن، پرسیدن سوالا میتونه به زبان فارسی باشه، نگران نباشین. اگر سوالی دارین نظر دکتر بپرسین تا این مرحله،
یا میتونن نگه دارن آخرش، من سعی میکنم 10 دقیقه تمام دیگه.
خب اگر سوالی دارین هم میتونید خودتون میکروفوناتون رو باز کنید، خود دست خودتونه دیگه. اگر هم میکروفون ندارید و خیلی سوالتون ضروری میشه توی این قسمت پیام بنویسید تا ما از طرفتون بخونیم. حالا شاید هم میخوان آخر کار. آقای دکتر موحد شما سوال دارین؟
من عذرخواهی میکنم این وسط. آرمان بگید لطفاً اون منوبار پایین رو هاید کنه. عذرخواهی میکنم. من
اینو
چهار 17 سلام. آره 4 17 سلام.
خب آقای دکتر فکر کنم ادامه بدید.
بسیار اوکی. خب میریم سراغ بخش future perspective. This part I don't talk much about cosmology, but I just try to show that how things are developing from now. And I would say that it's like a hiccup, it's like a big step forward. From the science perspective, as I said, we are dealing with the two key questions. One is the power law, primordial power spectrum, and there is a lambda dark energy. These are the same question we had in last years. But yes, we are still dealing with that. But now we know that there is a high possibilities for systematics in different data. We need measurements, and we have also technological challenges. So maybe this talk, this series would be more interested about these technological challenges, which I try to little explain. So by the new wide field area digital cameras on large telescopes like LSST, which has changed the name to Vera Rubin, we are going to generate an immense amount of the data. Okay, so think about that the telescope like an LSST is equipped with a 2144 megapixel camera. Okay, so it is like a 3000 megapixel camera. And that with the new phones, each picture we take with, or I don't know, 8 or 10 megapixel camera, has like a few megabytes information. Imagine that you are using a 3000 megapixel camera, and so you are basically producing kind of an unbelievable amount of information. And with this amount of information, old style astronomy is simply not possible, and because we need to deal with the big data. And it is not wrong to say that with the near future surveys, the data volume of a whole survey of the early 2000s is going to be generated in just one single night. So imagine that we are talking about let's say SDSS1, the whole survey data is just one night of the Euclid or TMT or LSST. And so we cannot really follow the conventional analysis that some students go there, collect the data, come, download it, analyze it, for 6 months and write a draft and paper. No, I mean, during 6 months, like 180 times more data have been around. And so it is beyond the capability of the community to analyze this data, because the size of astronomical community has not become orders of magnitude larger, right? And the capability of human being by evolution or whatever is not going to change like that. So we need machines to help us. And in this challenge, a real-time analysis is largely essential, because even storage would be very difficult. Imagine that every day you generate like terabytes of the data. So by generating terabytes of data, you would not have even cooling facilities to just cool down your computers who are just storing your data. And storage is one point. Another point is even to transfer the data. You need your specific fiber optic to just connect your telescope to somewhere. And then, okay, what about from that somewhere? Let's say that data from telescope go to one of the bases in one of the universities. How about the collaborators in the other universities? So it is a very difficult problem. And as I said, just storing the data, just transferring the data requires lots of computers. Even cooling system for these computers may be very costly. You need a real-time analysis. And so computers and algorithms must do most of the works. In particular, it demands certainly a very efficient and accurate machine learning training and imaging algorithms. Because again, let's remember and let's consider that if the algorithm we are developing has some caveats, and it can introduce new sort of systematics to our analysis. So far we talked about all those weird systematics which we can have in different observations, but one problem with using some of these algorithms is that they can introduce systematics. Systematics are difficult to find. One thing is certainly clear, and is that astronomy can become a great domain for research in computer science, and I think that would be certainly an opportunity for astronomy to help the computer science, at the same time get help from the computer science. So what is ahead? Just as some example, this is a very large telescope of the ESA that like 20 years ago. This is SCSS. This is another survey, Vista, and this would be, for example, LSSD. And you see that the LSSD suddenly generates like 150 times larger volume of the data than the SDSS. And then we have TMT of the same order. And remember that LSSD form of the data would be also different, because the SDSS was kind of a spectroscopic data, and the LSSD would be practically like a photometric. So it needs to be processed. We need to look for many things. And in last 20 years, we certainly, we don't have 150 times more students, and or capability of human didn't increase much. So we need better computers and better analysis. SCSS, as I said, was a pretty successful survey. I was a member of that. We had this paper, and it was very largely covered very recently. It was even the CNN and all news agencies, because it practically produced the largest 3D map of the universe so far. And so it is interesting and fun. But and it also had about more than 200 galaxies and more stars were detected by the survey. So these are a large number, but this is just nothing comparable in comparison with the future surveys, near future surveys. So you realize that okay, we are the tsunami of the data, and we cannot do surfing on the tsunami. We need to do things in a different way. Just little explanation about the astronomy data. We have two major forms of astronomy data. One of the spectroscopic observations, we are measuring flux at many wavelengths with high resolution, like this one, which I got from the SCSS website. And we have photometric observations, that we are taking images using films, which is prehistoric or CCDs, through broadband filters. This is just the sensitivity of the filters I've shown here in this plot. That you are just averaging over all those frequencies. So it has some information, but it's easier to achieve. And by this kind of but future of astronomy basically have both of them. One of the important ones would be LSSD on the imaging, and for the spectroscopy we have the DESI. The future perspective for the type 1a observations I'm just trying to show here is that, remember that we have 1,000 type 1a supernova, 1,000. And this is what we achieved in last 30 years. Our biggest compilation is just 1,000 supernova. And this is what we expect to get in 2020s. Means that in the next 10 years, we are going to observe this amount of the data. At the very low redshift, we are going to have about 10,000 supernova, just at the low redshift, which is coming from the help of many different surveys, from the Pan-STAR to Zwicky transient facility to LSSD, and it is amazing. We would have about 2,000 detection per year, and and some of them would not be confirmed, but we would get about more than 1,000 or 15,000 supernova just at the redshift less than 0.1. At the intermediate redshift, basically between redshift 0.01 and 1, we are going to observe about 300,000 supernova type 1a, 300,000. So this is crazy. I mean, this is too much. And many of them will be confirmed spectroscopically. And so that basically, will give us an opportunity to really study well how things are really going on in the universe. And also at the high redshift, you would have about few thousands, up to 5,000 to 6,000 high redshift supernova. At the moment, we have just handful. We have like 20, 30 of them. So things will be dramatically changed. But this also allows us for a new kind of physics to do, and this is about a strong lensing time delay cosmology, which can be done by the supernova as well. And that would be very precious because unlike the quasars, that people do the time delay analysis, including me, myself, and my ex-postdoc Amir Agha Musa, who left academy. So we did lots of analysis on the quasar lensing, but what is interesting that we can do it with the supernova. And supernova, since it has a very specific feature, that would be very interesting, and it can be, you know, and the source can be very high redshift. So this can also allow us to have lots of new kind of information, which even handful of them would be very important to give us valuable information about the background cosmology. So these are some of these are a very recent paper that we wrote with my current postdoc, Sata Jubag, and two of my LBNL collaborators, like long-term collaborators, Alex Kim and Eric Linder, that we try to have a very ambitious approach. So when I said about the type 1a lens supernova, means that, you know, you have a supernova which is lens, so that the information is coming from two different paths. If the distance, if the time delay between these two different passes are long enough, let's say in this case the time delay is of order of 42 days, then you can see two different peaks, and these are different bands which you're observing. So it is easy to say that, okay, I have a lensed supernova. Remember that you don't see two different paths. You see everything on one pixel in your detector. But in your detector, you see that things are going up and down. So you may basically infer that, okay, it looks like that, you know, I'm observing a lensed supernova. That this peak is the peak from the one path, and another peak is from another path. So there is a magnification and there is a time delay. But what is difficult is in this case that, you know, the time delay is small. And it just looks like a one curve, but it is in fact coming from the two curves. So this was a very ambitious problem, which we tried to see what we can do. And Sata practically spent a year working on that. And people who work with me, they know that usually, you know, they have to work a lot. And I think Sata did a huge amount of effort to make this work. But we see that it did. For example, you see all these. So we didn't care about those light curves which has two peaks there, but which have such a shape. You know, we could basically find out that this one is basically coming from the combination of these two shapes. This one's coming from these two shapes. So we had a very good result in finding the actual time delay, and actual time delay as well as the magnification. Of course, a very complicated algorithm. We had like 30 degrees of them. We used Hamiltonian Monte Carlo approach, and so we did lots of magics and tricks. But I would say that, you know, I liked our results because for many cases we could get the true time delay very well, particularly for the cases that the time delay is more than about 10 days. We had no problem. Less than 10 days, we had some problems. I would say here that, you know, in all the works which I do test the algorithm blindly. Means that I have a serious problem with the people who just data and then they model and show that everything is great. So always within the collaborators, someone is generating the data. When we are based on algorithm, someone basically did the data and sent to us, and we try to test it blindly. And so these are all blind analysis, so which we show that, you know, we have no outlier. So this is about the imaging that, you know, like a supernova, that what we can do, and a kind of a work that people can do, which are interesting. I expect that we would have few hundreds of such cases in the next 10 years, but each single case can be very, very rich in information. In the case of the spectroscopic surveys and the galaxy surveys, this is the number of galaxies, number of the redshift galaxies from the different surveys. So we have one of the first surveys, CFA, which they looked at about a few thousand galaxies in early 80s. Then we have the, you know, CFA2, for example, here, which was early 2000. We had about a few tens of the galaxies. Then we had the SDSS. And SDSS basically was a big rip in the analysis. So we have like a few hundred thousands. Remember that your your y column is your y axis is practically logarithmic. So SDSS basically allows us to have few hundred thousands, close to 1 million redshift measurements. So it's not only about the detection of the galaxy. Basically, the galaxy was detected so well that we could measure its redshift very accurately. So this is SDSS 3 and 4, which we went to the EBOS, and the EBOS practically allow us to have few million galaxies. And this is about the DESI. DESI is what, again, I'm a member, one of the PI of the DESI, and the dark energy spectroscopic instrument. It is going to function soon. DESI would be actually the first fourth generation of the cosmological observations which is going to run. It will be earlier than the Euclid and earlier than the LSSD. And in some sense, there's a huge competition between the DESI and Euclid, because I personally prefer DESI because it's earlier. So Euclid data would be more rich, but DESI is earlier. And the similar argument which I say is that imagine that we want to do fishing, and there is a big pond, and I know that there are some big fish, or there might not be, but if there is a big fish, even with my more simpler equipment, I think it's better to be there earlier, because I would still have a big chance to catch the big fish than getting to the lake later and having a more fancy equipment. So in that sense, I think DESI is has a bigger chance than the Euclid, which is a space satellite, and the PFS, which is a spectrograph launched on the Subaru telescope to catch the big fish if there is. And this big fish is practically evolving dark energy. But as you know, people do not just stop where the next plan is, so they think about the next plan. So already people who have been working on the DESI, many of them are now proposing a proposal called the Mega Mapper. So Mega Mapper is already proposed as one of the 2030s surveys, which is a very optimal telescope in the sense that Mega Mapper is saying that, okay, I want a bigger telescope. This is a 4-meter telescope. And they said, okay, Magellan telescope. They don't confuse Magellan with the giant Magellan telescope. Okay, GMT is one of the 4.5 generation. It's a 25-meter telescope. Magellan is something which is running at the moment. It's a 6.5 meter. But the DESI people, or many people involved with DESI and some others, they are saying that, okay, let's launch and install an spectrograph on the Magellan and change it to a spectroscopic survey. And that would be very competitive because, 6.5 to 4, the area would basically more than double. And instead of 16 spectrograph, we can have 32. 16 instead of 10 spectrograph, we can have 32. So DESI had 10 spectrograph. Each spectrograph had about 600 fibers, but here we would have a huge amount of fiber, much more. So yeah, and then Mega Mapper would allow us to continue on this logarithmic line, and having about more than 10 to power 8 means that few hundred millions of the redshifts means that we are observing these galaxies with the redshift, and we can go very deep. We can go to the redshift higher than redshift 2. So this would be a huge achievement. However, there might be some caveats to the Mega Mapper because if it is really lambda dark energy, Mega Mapper would not find anything either. So it's very much focused on this topic. So it might be a caveat for the Mega Mapper to be approved by the agencies. So some comparison of the future surveys. So SDSS, let's take SDSS and BOSS as the base, and let's compare the other ones. So these are the primary meter size that per meter square. So SDSS was about the 4 meter square. It was a 2 meter telescope. DESI would be 9.5. PFS is 50. Mega Mapper would be 28. But then the field of view is comparable in many cases, 7 degrees square. So it's a very wide field, right? 7 square degrees is really wide. Reflections are very good, at the order of 1. And the product is practically a combination of all these things together. Which basically says that how much light practically is coming to your instrument. But when we compare the spectroscopic surveys, it is better to have the products in another term, which is basically multiplication of the size of the telescope, the area of the mirror, into the number of fibers. These are the fibers that we are basically collecting the information. And this basically gives us much better understanding of how much would be the product with respect to each other. and the speed is something that we are scaling them all to. all to SDSS. So SDSS is 1. Then we can see that, you know, the bus was 1.6. It was still the same telescope with just, you know, some modification. Practically, they added the number of fibers. And the DESI would be 22.4. So you can see that suddenly, you know, we are improved by about 15 times. PFS would be double than the DESI. And the mega mapper is suddenly 238. So by having just a slightly larger telescope and by mounting more fibers, so instead of, you know, in DESI we have 5,000, here we have 20,000, we can, you know, increase the speed up to like 10 times. And don't forget that, you know, the amount of information, amount of the data which is produced would be also increased by the same order. So at the moment we are here, we are, let's say, okay, maybe with the E-bus, we are not 1.56, we are, let's say, 1.2. But with the DESI, we are going to be 20. So we have 10 times more information. So at the moment, the information sometimes is recorded on the tapes, and the tapes are brought up because they're even faster than the fibers. But yeah, I mean, the amount of information would be huge. But let's not forget that still, DESI is not a survey that we worry much about the data, but the others like LSSD or TMT would be, or GMT would be the ones which we have to seriously think about the data transfer. The future perspective would be very good science-wise. You know, we have basically very good you know, measurements of the expansion history by these surveys. Things would be really great. You know, we can get lots of, you know, good results, hopefully. We can basically do redshift space distortion and get a good constraints on the gravity growth of a structure. In the form of the premodal spectrum and CMB, you know, we might have the S4 missions. None of them yet confirmed, like Coral, which was like a cosmic origin explorer by the ESA, was not accepted. But I think Japanese have a Lightbird, you know, so I think Americans are pushing for a survey. So if it comes again, we are going to deal with the, you know, a very good, rich amount of information from the cosmological background. Hopefully, a full sky polarization data. Another important thing is that to take large structure data more seriously, practically, you know, trying to, you know, really analyze the data in 3D, and so which opens up lots of opportunities for new developments, algorithmic developments. And one of the things that I am doing with my group and some of my ex-members, like Benjamin Louillier, who have been to Iran actually for one of the IPM workshops, is to do power spectrum. I mean, instead of power spectrum or bispectrum, we try to do some more, you know, innovative approach and trying to distinguish between models that, you know, we cannot really distinguish by the conventional ways, like a two-point correlation function or power spectrum, and practically comparing and analyzing the 3D information. So in this work, which we published last year, you know, Benjamin used a huge amount of simulations. It was like a 2,000 CPU hours using KISTI facilities. KISTI is an institute in Korea which practically support scientists with the computational power. So people write proposals, and there is a team to evaluate the proposals. If they are sound, if they have a good history, they just grant you some hours. They give you an account, you know, and then you can just compile your codes. They have lots of technicians and engineers who keep the system very much, you know, active and without any bug. And so it is working very well. In fact, it is something that I have suggested to my colleagues long ago in Iran. And I really don't know what is the situation, but that could be something certainly very useful to have a computation center, just purely computation center, and biophysicists, geneticists, physicists, astronomers, chemists, whomever, you know, who is, you know, have large simulations, write a proposal, go there, get some time and run their code. I think such a center would be certainly essential, as many countries have this. Anyway, so we use about 2 million CPU hours. Now we are using about 5 million CPU hours for some extended analysis. And we made like 100 DESI-like simulations to compare things and test our statistics. And one of our main points was advocating against reducing the dimensionality of the data for model selection. I would say that in this line, what we are doing now, which is very interesting, is about the 3D convolution neural network. So you know that the machine learning and CNN is becoming very popular. So we are trying to be a little, again, innovative here and we are trying to basically use the whole 3D data to do that, and the 3D convolution is a little expensive, but we will see. We hope that we can achieve that. Okay, so my last slides. Cosmology versus systematic versus assumptions. With higher quality of the data, the role of systematics will become more and more prominent. This is one of the main concerns of the future. But while handling large flow of the data is essential, we should also avoid introducing new sort of bias in the pre-analysis. So it means that if we are using an algorithm to pre-select us some of the data, that algorithm should work really well. And if it doesn't, that can introduce different kind of biases. That biases might be interpreted as a new physics. So dealing with the big data is not only about handling it or storing it or transferring it, but the algorithms which we developed, they should be fiercely tested before used in the pipelines. And the higher precision and the bias are something like a very big enemy of each other. Let's remember that when we have a lower precision, things are okay if we have little bias. But if you have a high precision, little bias can destroy everything, and this bias can come also from the wrong assumptions. So the final slide, the standard model of cosmology looks fine. So cosmology, the standard model and cosmology looks doing well, but there are tensions, and these tensions have not been explained. And we might look for the tensions and some new physics or some systematics. Technological challenges are important and part of the future astronomy. I would say that still many surveys don't have a clear plan how to deal with all those things. And but I think they will eventually do. We have to rely on machine algorithms, so we have to make them accurate. So it's very important. This is again something that we have been working on with some of my collaborators to train an algorithm to correct itself and increase its accuracy. So, which is a very interesting practice, I would say. It is highly possible that there are systematics in some of the data. So, new independent measurements and observations are essential. So, we hope that we can get there. We have surveys. So the next 10 years would be very crucial because we have DESI, Euclid, LSSCW first. SKA, no, they don't get to this decade, but with these new surveys, which are just going to launch sooner or later, probably we'll have a better understanding of the status of concordance model in 2020s. It would be a bit pity if the model remain as what it is. But if it doesn't, if we find some deviation or if we find that we should go beyond this model, then that would be very interesting, and that would give us some hope that we might even be able to plan for the larger surveys and continue with this massive and interesting journey to understanding the cosmos. Yeah, thank you.
خیلی ممنون آقای دکتر شفیع. خب خدمت دوستان هستیم. حالا تا دوستان آماده میکنن سوالاتشون رو، من این یک آقای نامدار یه سوالی پرسیدن که به نظرم شاید جالبم باشه. سوالشون در مورد این CCD های نسل جدیدیه که برای این اندازه‌گیری های کیهانشناسی استفاده میشه و یک هم پرسیدن که مثلا رو خود این CCD های نسل جدید رو مکانیسم اندازه‌گیریشون در واقع امکانش هست اطلاعاتی بیشتری بفرمایید.
سوال بسیار خوبیه، ولی فکر میکنم که متاسفانه من آدم مناسبی برای جواب دادن به این سوال نیستم. اطلاعاتم محدوده. مثلا در مورد LSSD من آخرین باری که استیو کان مثلا صحبت از این بودش که این CCD ها چیز خیلی کمتر دارن، فلا خیلی کمتر دارن، یعنی بخشی از این CCD ها که امکان داره اطلاعات رو کمی غلط منتقل بکنن بسیار کمتر شده، افیشنسیشون رفته بسیار بالا. ولی اینکه اعداد دقیقشون چیه یا چه متریک استفاده میکنن تا عملکرد CCD رو دقیقاً مقایسه بکنن با نسل قبل میتونم پیدا بکنم، ولی در حال حاضر و الان واقعا اطلاعات دقیقی ندارم. بهتره که جواب درستی ندم وقتی نمیدونم. ببخشید.
خواهش می‌کنم. البته خب ما نبایدم توقع داشته باشیم این سوال رو جناب عالی جواب بدین، چون شما آنالیز میکنید، محاسباتی کار هستید. ولی خب حالا کنجکاو بودن.
آدم بدون خوبه میدونین، ولی خب سوال خوبیه، یعنی من حتما اینو یاد خواهم گرفت دفعه بعد یکی از من سوال کرد بتونم جواب بدم.
یکم بیشتر هم توضیح دادن اگر میخواید بعد تعاملی بفرمایید. میگن که CCD های قبلی مکانیسمشون کامپتون بوده، عملکرد فیزیکیشون بر مبنای روش کامپتون هست و حالا پرسیدن که آیا مثلا اینا مکانیسم جدایی دارن. خب دوستان دیگر هم میتونن صحبت کنن اگر امکانات دارن، هم میتونن بنویسن، من به جاشون بخونم و به هر صورتی که علاقه‌مند هستید بفرمایید سوالاتونو.
خواهش می‌کنم. اجازه هست من سوال
بله صادق جان بفرمایید.
خواهش میکنم. متشکرم آرمان جان. عذرخواهی میکنم. من تشکر میکنم از سخنرانی خیلی خوبت و همچنین از دوستان و سایر دانشجویان و همکاران که شرکت کردن. من یه دو تا فکر کنم سوال کلی دارم که حالا بعد اگر نیاز شد جزئی‌تر مطرحش بکنیم. ببینید شما یه بخش صحبتتون در خصوص حضور این تنشن و مواردی که به خصوص تو این سالهای اخیر تو حوزه کیهانشناسی مطرح شده و افراد مختلف و گروه‌های مختلفی از جنبه‌های مختلفی تلاش کردن که این مسئله رو بررسی بکنن. شما هم خودتون در واقع تجربه داشتید، هم تو بخش مدل سازی و هم تو بخش در واقع پرداختن به حوزه‌ای که ممکنه این تنشنال لزوماً مفاهیم در واقع عمیق علمی نداشته باشن و مسئله سیستماتیک باشه. حالا من یه سوال کلی که یک دیدی بده به مجموعه حالا افراد تحقیقاتی که توی ایران دارن کار میکنن توی مسئله تنشن، حالا خصوصا مورد H0 تنشنی که وجود داره الان توی کامیونیتی بین‌المللی و همچنین تجربه خودتون بیشتر تو کدوم جهت مردم دارن تلاش میکنن برای حل این مسئله؟ آیا تلاششون روی صرفا طور قابل توجهی روی مسئله مدل سازیه که برن مدل های مختلفی رو جایگزین لاندا CDM معرفی بکنن، یا تمرکزشون یا بخش قابل توجهی از تمرکزشون رو مسئله سیستماتیک رفته، یا اینکه کلا اصلا ما باید بریم دنبال یک نیو میجرهایی و به قول معروف معیارهای جدید که حسب اون معیارهای جدید شاید اصلا این تنشن‌ها وجود نداشته باشه. این یه سوال کلی که فکر کنم حالا یه توضیح بده، من دوباره سوال دومم میپرسم.
باش. خب صادق جان، منم بسیار خوشحالم که با هم صحبت میکنیم بعد از مدت‌ها. جواب دیپلماتیک میخوای یا جواب صادقانه میخوای؟
Both of them.
خب جواب دیپلماتیکش اینه که به هر حال مردم دارن سعی میکنن که ابعاد مختلف مسئله رو بررسی کنن و ببینن که مشکل از کجاست، ولی جواب صادقانه‌اش اینه که در واقع هر کس داره کار خودش رو پوش میکنه. ببین الان مثلا استاتیو به خاطر اینکه به هر حال علاقه داره به مدل استاندارد، تمام سعیش رو داره میکنه که یه ایرادایی پیدا بکنه تو کارهایی که تیم آدم ریس داره انجام میده. حتی مثلا تو همین مدت هم مثلا این مقاله نوشته و نشون داده که مثلا دو تا از اون انکورایی که در واقع از استفاده میکنن برای اینکه کالیبریت بکنن سفیدا رو، اینا مثلا با هم دیگه تنشن داره، در نتیجه مثلا آنالیز ریس امکان داره درست نباشه و شاید نباید خیلی تراست کرد به جوابایی که ریس انجام داده. ریس از اون ور برمیگرده میگه که نه ما دیتا هامون این کارو نکردیم، حتی اگرم اون مسئله رو در نظر بگیریم، حالا فرض کن 74 نمیشه، میشه 72.5، یعنی خیلی مشکلی رو حل نمیکنه. باز هستن کسایی که میگن دیتای ریس رو کسی نمیتونه آنالایز بکنه، در حالی که خود ریس میگه نه، دیتای ما اویلیبل، حتی دانشجوی بچلر هم میتونه دیتای ما رو برداره و آزمایش بکنه. واقعیتش اینه که سخت آدم بفهمه که چه مقداری از این مسئله ایگو و مسئله علایق شخصیه بخواد به اون کاری که کرده انجام بده و چه مقدارش واقعا ریشه در حقیقت داره. ولی واقعیتش اینه که این چالش ها باید وجود داشته باشه تو واقعیت بیاد بیرون. همینطور جای دیگه، ببین مثلا وقتی که ACT مثلا میاد دیتا میده، ACT کاملا سعی میکنه که با پلانک هم خون باشه جواباش، برای اینکه اگه نباشه اون وقت باید ببین که حالا دو تا میجرمنت CMB هم با هم دیگه در تضادن، یعنی جوری اینا قشنگ ماساژ میدن دیتا رو تا حد خوبی که حداقل تا جایی که میشه تنشی توی دیتا وجود نداشته باشه. یه مثال سادهش تو همین مثلا مقاله آخر STSS که میگم من هم جزو نویسنده‌اش هستم، مثلا تو این پلات خب من اینجا دارم مشکل میبینم. ببین این BAO داره یه جای پارامتر فاز پارامتر نشون میده، CMB داره یه جای دیگر رو نشون میده. خب این مشکله، ولی خب واقعا مشکل داشتیم که بخوام اینو توی مقاله خیلی واضح بیان بکنیم، برای اینکه مردم ترجیح میدن که مشکلات کمتر باشه و دوست باشن با هم دیگه و اینا. حالا اینکه مشکل واقعا کجاست و اون چیزی که شمه من چی میگه، من خیلی جدی به این فکر میکنم که امکان داره که تنش‌ها چند ریشه داشته باشه. یعنی ما نه فقط دنبال سیستماتیک تو چند تا از دیتا باید بگردیم، بلکه امکان داره به نیو فیزیکس هم احتیاج داشته باشیم. ولی خب بهتره که چشممون باز باشه، ذهنمون باز باشه و صبر کنیم ببینیم چی میشه دیگه. یعنی من همه احتمالات رو محتمل میدونم، ولی خب به شخص خودم الان دیگه با استاندارد نیستم. به شخص خودم ترجیح میدم که واقعا مشکل داشته باشه استاندارد مدل، بلکه مدل مثلا دارکنش خودم رو دارم و دوست دارم اون کار بکنه، ولی خب تو آنالیز کردن سعی میکنم صادق باشم، یعنی اون چیزی که آدم میگیره بگیره. این مثلا این مقاله گروه کامینیکوفسکی که خب تو پیارل هم چاپ کردن، یه مثال خیلی جالبه که وقتی که این آنالیز مثلا هیلتال اومد بیرون، خب فکر کنم اینا مشکل داشتن برای چاپ کردن مقالهشون، برای اینکه اینا در واقع اومده بودن گفته بودن که مدل پولینتال واقعا مسئله رو درست حل نکرده. خب اینا حالا تو پیارل هم چاپ کردن، نمیدونم کلی هم سایتیشن گرفتن، کلی هم کاورج گرفتن و خب یکی اومده گفته نه، ولی خب اینا مشکل داشتن تا یه حدی برای پابلیش کردن کارشون. برمیگم این بازی قدرتی که هست. در حال حاضر واقعا هیچ مدلی مسئله رو درست حل نکرده، هیچ مدلی. به صادقانه دارم میگم، حتی همین پدای خود ما همه مسئله رو حل نکردیم. میتونه دو تا دیتا رو جواب بده، سه تا دیتا رو جواب بده، ولی مثلا دو تا دیتا دیگه که اضافه میکنه جواب نمیده. و اینکه نمیدونیم واقعا مشکل از کجاست. ولی من حدسم اینه که احتمال داره که سیستماتیک وجود داشته باشه تو بعضی از این دیتا و اینکه شاید هم واقعا به نیو فیزیک احتیاج داشته باشیم. در حال حاضر باید جمع بکنیم، دیتا جمع بکنیم. یکی از بهترین چیزا اینه که دیتای کامپلیمنتری داشته باشیم. مثلا کوازارا و استرانگ لنزینگ یا تایم دیلی استیمیشن کوازارا میتونه بسیار مفید باشه، برای اینکه میتونه یه میجرمنت جدید H0 به ما بده. این دقیقاً کاری که اتفاقا منو یه سری از همکارام توی چین و همین کره هم داریم انجام میدیم که دو تا ابجلترز هم داشتیم روش، هم پارسال هم امسال، که در واقع به صورت مدل ایندیپندنت سعی می‌کنیم از تایم دیلی کوازار استفاده بکنیم برای حساب کردن ثابت هابل. و این خوبه برای اینکه میاد میگه که آقا من دیگه اون مشکلاتی سیستماتیک سفید داره ندارم، سیستماتیک متفاوتی دارم. حالا که این دوتا چون یه جواب بده خب خیلی بعید خواهد بود. در نتیجه احتیاج داریم به این کامپلیمنتری جوابات. توی CMB مثلا دیتای بهتر توی پولاریزیشن میخوایم، میدونیم که پلانک سروی تمپرچر بوده، سروی پولاریزیشن نبوده و خب نمیشه، شاید نشه 100% ریلای کرد به دیتای پولاریزیشن پلانک. در حال باید دیتای جدید بیاد. در حال حاضر فکر کنم بهتره که آدم خیلی اوپن مایند باشه و همه آپشن‌های مختلف رو در نظر داشته باشه. ببخشید اینقدر طول این جواب دادم.
دست شما در نکنه. درود. یه نکته اینجا مطرح کردی در خصوص کیهان شناسی مبتنی بر 21 سانتی متر تابش 21 سانتی متری چی؟ الان ما مدتی خیلی تو این جلسات نبودیم، در واقع اطلاع دقیق تری داری که پیشرفت قابل توجهی داشته به عنوان یک درگاه و یک پنجره جدید؟
ببین صادق جان، دارن مردم روش کار میکنن ولی سرعت کارشون خیلی کند بوده. ببین 21 سانتی متر قرار بود که در واقع فلگشیپش بشه SKA، درسته؟ ولی SKA حتی فاز یکش بعیده که تا آخر 2020 یعنی 2020 دهه 2020 بیاد. خب و وقتی اینقدر طولانی باشه، من خودم به شخصه مثلا یه نیمچه درفتی 2016 نوشته بودم مثلا فورکست SKA، ولی دیدم نه، مثل این که اینا واقعا دیتایی در کار نخواهد بود حداقل تو 10-15 سال آینده. و واقعا الان تا 10 سال آینده دیتای SKA که قابل استفاده باشه برای کیهان شناسی در دسترس نخواهد بود. من نمیگم کار خوبی نیست، منم اتفاقا تو همون کاسی تو هم گروه کیهان شناسی دیوید پارکینسون مثلا روی این کار میکنه. من سعی میکنم خیلی نگاتیو نباشم، ولی واقعیتش اینه که من هدف اصلیم از کیهان شناسی پیدا کردن یه اطلاعات جدید نسبت به عالمه و نه فقط کار کردن روی دیتایی که حالا قراره 10 سال 20 سال دیگه بیاد. برای همین تمرکزم بیشتر روی دیتاییه که زودتر خواهد اومد. درنچه دزی، اوکلید، LSST اینا دبلی فرست اینا مسلماً دیتایی این که زودتر خواهند اومد و رقابت میکنن با هم دیگه. SKA فعلا توی کانشناسی قابلیت رقابت نداره. نه تنها SKA باید که تمام اون پتفایندراش، تمام اون کسایی که توی تیانله یا توی مثلا ساوت افریقا یا توی استرالیا دارن کار میکنن روی اون به قول معروف سروری که کوچیک‌ترن، اینا قابلیت رقابت پیدا نخواهند کرد برای کانشناسی.
متوجهم. یه سوال کلی دیگه اینجا بپرسم.
آقای دکتر
من عذرخواهی میکنم، دلیلش اینه که میخوام
چون یه نفر دیگه هم دوست دارن صحبت کنن، میخواد ایشون یک صحبتی بکنن.
بله.
آقای دکتر قمصری هم مدتی است که ببینم میتونن صحبت کنن، اگر نتونستن باز خدمت شما باشیم.
سلام دکتر،
سلام علیکم، بفرمایید.
خسته نباشید دکتر شلو و سپاس از سخنرانی شما. من بنا به زمینه کاریم که خب دکترا ماده چگال بوده و حالا یه زمانی هم توی زمینه‌های ژئوفیزیک کار می‌کردم، دو تا ایده‌ای که یعنی یه مجموعه ایده‌ای که توی ذهنم هست و به درد این مدل سازی‌ها می‌خوره می‌خواستم با شما در میون بذارم. یکی به همین نکته که شما فرمودید می‌خوام اشاره کنم که مثلا گفتین که دیتاهایی که میان یه جورایی به خاطر اینکه میخوان ادب رو رعایت کنن یا با هم دوست باشن که در توافق باشن، ولی اتفاقا اختلافی که بین اینا هست و اگر وجود داشته باشه میتونه به ما یک اطلاعات دقیق تری از اون فرنل زونی بده که ما اطلاعات رو کشیدیم ازش بیرون. یعنی بنا به تئوری‌های توموگرافی در واقع این کار دیگه، یعنی عملا یه توموگرافی داریم انجام میدیم که فولد دیتایی که داریم از یه ناحیه فرنل میگیریم رو افزایش بدیم تا سیگنال به نویز افزایش پیدا کنه. در واقع این پارالاکسی که بین دیتاهای دو تا در واقع ماهواره هست یا حالا دو تا تلسکوپ هست، هر چند کم شاید بتونه فولد ما رو افزایش بده. این کار رو مردم توی زمینه‌های مختلف توموگرافی انجام میدن، اهم از ژئوفیزیک. شما وقتی CT اسکن میکنید، MRI میگیرید، در واقع یه سوروی دیزاین دارید که میگید که من با چه آرایش و ارنجمنتی از کجا به کجا موج بفرستم یا دریافت کنم که این پارالاکسش فولد رو افزایش بده. بعد خود عملیات هست، بعد پردازش و پروسسینگ هست و بعد تفسیر دیتا هست که خب قاعدتاً این یه روند اینورس مدلینگ با روندهای ایتریتیو و برای اینورژن همراه هست. یکی این هست که یه نکته که خواستم بگم که آیا میشه از رو دست کسایی که توموگرافی کار میکنن به طور خلاصه بگم نگاه کرد و یک کمی ایده های جدیدتری برای الگوریتمامون به دست آورد که راحت‌تر بشه این حجم دیتا رو تحلیل کرد. یک نکته دیگه اینه که دوباره بریم از دست یکی دیگه نگاه کنیم و ایده نرد الگوریتم، حالا بریم زمینه پارادایم تئوری و نظریه پردازی کار کنیم. اون قسمتی که شما میفرمایید که آیا فراتر از لامدا CDM باید رفت یا نباید رفت، بحث اینه که اگر بگذاریم که جامعه علمی دموکرات باشه، خب شاید بشه رو دست ماده چگالیست ها هم یه چیزایی رو کپی پیست کنیم، حداقل ایده بگیریم، ببینیم شاید اونجا پدیده های ایمرجنت رو یه جور دیگه توصیف بکنن. آیا این پدیده تریویال هست نیست، نمیدونم توپولوژی تریویال داره یا نداره، فیس ترانزیشن چطوری هست، منی بادی اینتراکشن ها و کوریلیشن ها چطور هستن. نمیدونم صدای من میرسه یا نه. من
بله صداتون هست آقای دکتر، بفرمایید. قطع شدم فکر کنم. خب میخواید جناب دکتر تو همین مرحله اگر پاسخی دارین، فکر کنم قطع شدن موقتا.
خب اگر خودشون نباشن که خب
یه لحظه اجازه بدین ببینم. یه لحظه.
نه من هستم. بله منظورم این بود که حرفم رو تمام میکنم. منظورم این بود که آیا میشه از تلفیق این دوتا ایده هایی که در پارادایم های خودشون جا افتادن هم استفاده کرد در این عرصه ای که حالا ما مشکلاتی داریم و شاید بتونه مشکلات رو حل کنه.
سلام آقای دکتر قمصری، از آشناییتون خوشبختم و ممنون از سوال خوبتون. نه بدون شک. ببینین من خودم اتفاقا علاقه خیلی زیادی روی بخش ایده کارهای جدید دارم تا اینکه آدم بخواد یه کاری دوباره انجام بده. و اینکه خب آدم واقعا باید یاد بگیره. نه من به شخصه دوست دارم از جای دیگه یاد بگیرم. بعضی از متدهایی که مثلا ما استفاده کردیم، مثلا گوشن پروسس رو که ما خیلی وقت داریم استفاده می‌کنیم، جز اولین گروهی بودیم که استفاده کردیم. در واقع ما این رو اولین بار از یه مقاله‌ای بودش که کس همکاریمون دیده بود، دقیقاً کسی بود که روی توموگرافی MRI کار می‌کردن و جی پی استفاده کرده بودن برای ریگرشن. و خب ما البته یه ذره عقب افتادیم از کسایی که توی دوسالاموس کار می‌کردن روش، گروه سلمان حبیب، ولی خب ما هم به هر حال جزو کسایی بودیم که تونستیم زود از جی پی استفاده بکنیم. ولی اینکه آدم باید واقعا چیز باشه، یعنی چشمش باز باشه و دنبال ایده‌های جدید بگرده. فقط یه توضیح رو سوال اولتون، اون مثلا بدون تنشنه که صحبت کردم، این تنشنه یه بعضی از وقتا میشه از این استفاده کرد برای پیدا کردن مشکل. مثلا اتفاقی که افتاده بود بین مثلا دبلیو مپ و پلانک بود که جفتشون دیتاهای کاسمولوژی بک‌گراندن، در واقع یک ماهیت دیتا بودن و اونجا راحت بود و استفاده هم شد و خیلی و واقعا سیستماتیک پیدا کردن توی مثلا 217 گیگاهرتز پلانک. ولی مثلا این کانتوری که من الان نشون دادم، اینا دو تا دیتا از خانواده بسیار متفاوتن. یکیش تابش زمین کیهانیه که ما در واقع اومدیم اسپیکال هارمونیکاشو حساب کردیم، اومدیم مدل روش فیت کردیم. یکی دیگه در واقع ما اومدیم اون مدل رو توی حالت بسیار متفاوت دیگه ای در واقع فیت کردیم به دیتایی که از دیستریبیوشن گالاکسی‌ها میاد. درنچه اینجور مواقع در واقع تمام این اطلاعات پروجکت شده روی فضای پارامتری که حالا ما وقتی این تنشن رو میبینیم دیگه اینقدر راحت نیست بدونیم کجای دیتا مشکل داره. ولی خب سوالتون در مورد اون که میشه استفاده کرد از این تنشن برای پیدا کردن مشکل موقعی که دیتا از یک نوع هست و این کارم میکنن مردم. خود ما هم این کارو کردیم. در مورد ایده هم که بدون شک، یعنی در مورد ریکانستراکشن، در مورد کلاسیفیکیشن، در مورد ریگرشن، حتی لیتموس تستا، در واقع تستایی که آدم میسازه برای اینکه یه مدلی فالسیفای بکنه، باشه جای دیگه ایده‌ای خیلی خوب خواهد بود. اگرم شما ایده‌ای دارین من خوشحال میشم برای من بفرستین یه چند تا رفرنس.
بله بله.
خب دکتر موحد شما میخواید پس سوال اگر داشتید به عنوان آخرین سوال. آقای دکتر انصاری بفرمایید. خواهش میکنم.
ممنون از آقای دکتر شفیلو. من سوالم چون بیشتر احساس کردم که CMB رو حالا خیلی سریع ازش گذشتید، یعنی ما میتونیم در واقع فکر بکنیم که پلانک یه جورایی در واقع آخرین رصد مهم ما تو CMB یا نه، مثل همینطور که تو لارج اسکیل شما خیلی ازش مثال زدید، CMB هم آینده ازش آزمایش‌های مخصوصا تو الهای بالا مثلا میتونیم انتظار داشته باشیم که آزمایش ببینیم، دیتا ببینیم. یکی این، و اگر حالا به نظر میرسه که تمرکز بیشتر رو قسمت لارج اسکیله، سوالم این بود که از نظر تئوری در واقع تشکیل ساختارها که مثلا حالا ما تو لوکال احتمالاً کهکشان‌های زیادی رو خواهیم دید، بعد شاره مثلا حرکت این کهکشان‌ها چه شکلی خواهد بود و چقدر توصیف تئوریمون قویه که بتونیم این مثلا حالا نتایج این داده ها رو بخوایم توصیف بکنیم.
خب ممنونم. در مورد CMB صدای منو دارین؟
بله دکتر داریم.
بله.
در مورد CMB ببینین واقعیتش اینه که نه، واقعا میشه خیلی جلو رفت. ما توی لو الا، توی الای پایین یا توی اسکیلای پایین در واقع نمیتونیم بهتر کنیم سیستم به خاطر اینکه کاسمیک واریانس داریم. یعنی به جایی میخوریم که بیشتر از اون نمیتونیم، ابعاد عالم از اون نمیتونه بیشتر بشه، رایت؟ به کاسمیک واریانس میخوریم. ولی توی الای بالا نه، بدون شک. علت این که من زیاد راجع به CMB صحبت نکردم اینه که هیچ S4 میژنی در حال حاضر اپروو نشده، تایید نشده. در واقع اگر مثلا کور اپروو شده بود بدون شک من 1/4 تاکم راجع به کور صحبت میکردم. منتها خب کور اپروو نشد و خب میدونین یعنی هنوز در حال حاضر ما هیچ اسفوری نداریم که بدونیم به صورت قطعی این کار خواهد کرد. بعدم این که ولی خب مثلا اکت پول رو داریم، اسپیتی پول رو داریم، در واقع گراوند بیسن ولی میخوان برن تو الای خیلی بالا. نه اینا مفید خواهد بود، موثر خواهد بود، ولی به نظر میاد که یک مقداری شیفت واقعا داره میره به سمت لارج استراکچر، برای اینکه متوجه بشیم که در واقع از این دیتا استفاده کنیم، چون دیتا واقعا و عظیمی هست، میدونین، یعنی دیتایی هستش که به مقدار بسیار زیادی میشه استخراج بشه. به این فکر بکنین که یک معدنی هستش که خب تا حالا خیلی ازش استخراج نکردیم و خب معدن بسیار بزرگی هست، یعنی هر چقدر ازش استخراج کنیم بازم داره. برای همین لارج استراکچر به هر حال قدرتش بیشتر خواهد شد. تا دهه قبل دهه CMB بود در واقع، یعنی ما بیشتر اطلاعاتمون رو از CMB میگرفتیم، ولی خب الان شاید یه مقداری موضوع فرق بکنه. در مورد سوال دومتون در مورد کار تئوری، ببینین کار با لارج استراکچر دیتا هم مشکلات خاص خودشو داره، به خصوص که ما باید مثلا گالاکسی بایاسی یا گروس رو خیلی تشکیل ساختار رو خیلی درست بررسی بکنیم و اینکه خیلی از وقتا مجبوریم که امبادی سیمولیشن انجام بدیم و این امبادی سیمولیشن ها خیلی از وقتا مثلا ساخته نشدن که برای مدل های خاص گرانش مثلا کار بکنن، یا حتی مدل های خاص دارک انرژی. این مقاله که مثلا ما فرباد حسنی بچهای ایران بود، مثلا سوئیس بود، این مقاله که با گروه اون داشتیم، یعنی من و بنجامین با مارتین کونس و فرباد داشتیم، دیگه همین بود، اینا اومدن سیمولیت کردن روی مدل خاصی از دارک انرژی که خب این متفاوته با لامدا و تخمین ها و تقریب های دقیقی که فرباد زد نشون داد که خیلی از سیمولیشن هایی که داره به صورت از مدل های نیوتنی استفاده میکنن درست نیست. در نتیجه واقعا از نظر بخش تئوری هم احتیاج به کار هست که این سیمولیشن ها رو هم بشه درست‌تر انجام داد که روی مدل های مختلف بتونه کار بکنه، یا برای هر مدلی شاید مجبور باشیم که کد مخصوص خودش رو بنویسیم. من به شخصه به خاطر اینکه هدف اصلیم به قول معروف فالسیفای کردن مدل ثابت کنشه، مدل استاندارد کنشناسی هست، خیلی دغدغه مدل های دیگر ندارم. خیلی بعید میدونم، به شخص حسمه، حالا نمیشه گفتم بیلی چیزشه، ولی خب بعید میدونم که گرانش چیزی فرای جی آر باشه. ولی خب قدم اول برای من همیشه اینه که آیا این مدل استاندارد هست یا نه، میدونین جی آر هست یا نه، اینکه حالا چی هست قدم بعد. برای همین خیلی دغدغه این رو نداشتم که روی سیمولیشن های مدل های دیگه کار بکنن، ولی خب این کار هستش که مردم دارن میکنن و باید بکنن. یعنی ما اگر دیتای خوبم داشته باشیم بخوایم مقایسه بکنیم با مدل های مختلف، باید بدونیم که اون سیمولیشن بر مبنای اون مدل به درستی انجام شده. ما نمیتونیم بیایم یه سیمولیشن غلط روی مدل انجام بدیم و دیتا رو پردازش بکنیم، چون نتیجه غلط خواهیم گرفت.
خیلی ممنونم.
خیلی ممنون دکتر که با حوصله جواب میدید. اگر اجازه بدید دیگه ما جلسه رو ختمش کنیم و به شرکت کنندگانمون هم اجازه بدین که اگر سوالی دارن تا چند ساعت آینده از طریق ایمیل اینا بپرسن خدمتتون، اشکال نداره.
ببخشید میشه یه لحظه‌تون نشینم، میشه بفرمایید؟
میگم بعضیا مکتوب یه چیزایی اینجا مینویسن به عنوان سوال، میگم اشکال نداره بهشون اجازه بدیم که تا چند ساعت دیگه از طریق ایمیل ازتون بپرسن این سوالاتو.
من مشکلی ندارم، همین الان هستم میتونم صحبت بکنم، همین که میتونن با ایمیل از من بپرسن، هر کدوم برای شما راحت تر.
یه مقدار جلسه‌مون دیگه طولانی شد، اگر بشه یه ساعت و نیم بیشتر نشه.
من رو ببخشید دیگه، به هر حال بچه‌ها با ایمیل برای من، ایمیل من فکر کنم داشته باشن، جواب خواهم داد اگر بتونم.
ما لینک سخنرانیتون رو از طریق سایت انجمن فیزیک در اختیار دوستان قرار میدیم. واقعا تشکر میکنم آقای دکتر شفیع، ازتون خیلی لطف کردید، سمینار بسیار مفیدی بود و از شرکت کنندگانمون از جناب عالی و بقیه دوستان خداحافظی میکنیم.
قربونتون برم، خداحافظ.
خیلی من قربان شما، خداحافظ. دوستان لینک سخنرانی امروز رو از طریق سایت انجمن فیزیک انشالله در اختیارتون قرار خواهیم داد و آقای دکتر هم اجازه دادن که این سوالاتی که مطرح نشد رو ظرف مثلا چند ساعت آینده از طریق ایمیل ازشون بپرسید. خیلی ممنون. خدا حافظ همگی.
خدا حافظ. دست شما درد نکنه.
خواهش می‌کنم. خدا حافظ.
سپاس. خدا حافظ شما.